According to the National Electrical Code, the cold water piping ground cannot be installed at the service panel. The cold water piping ground must be connected to the grounding electrode system at or near the point of entry of the water service into the building. Because the water service is located at the location of the service panel, the cold water piping ground must be connected to the grounding electrode system at that location. It is not permissible to install a conductor from the ground bar at the service panel back to the service disconnect to connect the cold water piping ground to the grounding electrode system. The grounding electrode system must be continuous and must not be broken by any conductors. The reason for this requirement is to ensure that the cold water piping ground is effectively connected to the grounding electrode system and that it can provide a low impedance path for fault currents. If the cold water piping ground is connected to the service panel and then to the grounding electrode system through a conductor, the resistance of the conductor could increase the impedance of the grounding path and reduce the effectiveness of the grounding system. Grounding electrode systems are designed to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses. This rapid clearing of faults minimizes the potential for electrical shock hazards and reduces the risk of fire. The grounding electrode system typically consists of several interconnected electrodes, including metal underground water pipes, ground rods, ground rings, and concrete encased electrodes, also known as UFO grounds. The primary purpose of grounding is to limit the voltage on electrical equipment and wiring relative to ground, preventing dangerous voltage build-up that could occur due to insulation failure or other faults. By providing a low impedance path to ground, fault currents can flow safely back to the source, tripping the overcurrent protection and isolating the faulty circuit. A properly installed grounding electrode system is essential for the safety of people and property, and it is a fundamental requirement of the National Electrical Code. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is developed and updated every 3 years by the National Fire Protection Association, or NFPA. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is intended to provide a minimum level of safety for electrical installations and to protect people and property from electrical hazards. Compliance with the NEC is often required by law, and it is essential for electrical contractors and installers to be familiar with its requirements. The NEC is organized into chapters, articles, and sections, each addressing specific aspects of electrical installations. Some of the key chapters include Chapter 1, which covers general requirements, Chapter 2, which covers wiring and protection, Chapter 3, which covers wiring methods and materials, and Chapter 4, which covers equipment for general use. The NEC also includes informative annexes that provide additional guidance and explanations of the code requirements. The NEC is a complex and detailed document, but it is essential for ensuring the safety and reliability of electrical installations. The grounding electrode system is a critical component of any electrical system, and it plays a vital role in protecting people and property from electrical hazards. A properly installed and maintained grounding electrode system provides a low impedance path for fault currents to return to the source, facilitating the rapid operation of overcurrent protective devices. This rapid clearing of faults minimizes the potential for electrical shock hazards and reduces the risk of fire. The grounding electrode system typically consists of several interconnected electrodes, including metal underground water pipes, ground rods, ground rings, and concrete encased electrodes. The selection and installation of these electrodes must comply with the requirements of the National Electrical Code. The metal underground water pipe is often used as a grounding electrode because it provides a reliable connection to earth. However, the water pipe must be in direct contact with the earth for at least 10 feet to be considered an effective grounding electrode. In addition, the water pipe must be supplemented by an additional grounding electrode, such as a ground rod or ground ring. Ground rods are typically made of copper or copper-clad steel, and they are driven into the earth to provide a connection to ground. The NEC requires that ground rods be at least 8 feet long and that they be driven into the earth until at least 8 feet of the rod is in contact with the soil. Ground rings are typically made of bare copper wire, and they are buried in the earth in a continuous loop. The NEC requires that ground rings be at least 30 feet long and that they be buried at a depth of at least 2.5 feet. Concrete encased electrodes, also known as UFA grounds, are made by encasing a bare copper conductor in concrete that is in direct contact with the earth. The NEC requires that concrete encased electrodes be at least 20 feet long and that they be encased in at least 2 inches of concrete. The grounding electrode system must be connected to the service equipment grounding conductor, which is a conductor that connects the grounded conductor of the electrical system to the grounding electrode system. The service equipment grounding conductor must be sized in accordance with the NEC, and it must be installed in a manner that provides a low impedance path for fault currents. The grounding electrode system must also be connected to the equipment grounding conductors, which are conductors that connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. The equipment grounding conductors must be sized in accordance with the NEC, and they must be installed in a manner that provides a low impedance path for fault currents. The proper installation and maintenance of the grounding electrode system are essential for ensuring the safety and reliability of electrical systems. It is important to consult with a qualified electrician to ensure that the grounding electrode system is installed in accordance with the NEC and that it is properly maintained. The grounding electrode system is a critical component of the electrical system, and it must be properly installed and maintained to ensure the safety of people and property. The requirements outlined in the National Electrical Code are designed to provide a minimum level of safety, and it is important to comply with these requirements to protect against electrical hazards. The primary purpose of the grounding electrode system is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers and fuses, which interrupt the flow of current in the event of a fault. Without a properly installed grounding electrode system, fault currents may not be able to return to the source quickly enough, which can lead to dangerous voltage buildup and potential electrical shock hazards. The grounding electrode system also helps to stabilize the voltage in the electrical system relative to ground. This is important because it helps to prevent voltage fluctuations that can damage sensitive electronic equipment. In addition, the grounding electrode system helps to reduce the risk of lightning strikes causing damage to the electrical system or the building. The National Electrical Code provides specific requirements for the installation of grounding electrodes. These requirements are designed to ensure that the grounding electrode system is effective in providing a low impedance path for fault current and in stabilizing the voltage in the electrical system. Some of the key requirements include the type and size of grounding electrodes, the depth at which they must be installed, and the method of connecting them to the electrical system. The NEC also specifies the minimum size of the grounding electrode conductor, which is the conductor that connects the grounding electrode to the electrical system. The grounding electrode conductor must be sized large enough to carry the maximum fault current that could occur in the electrical system. In addition to the requirements for grounding electrodes, the NEC also provides requirements for bonding, which is the process of connecting the non-current carrying metal parts of electrical equipment to the grounding electrode system. Bonding helps to ensure that all metal parts of the electrical system are at the same voltage potential, which reduces the risk of electrical shock hazards. The NEC specifies the minimum size of the bonding conductors, which are the conductors that connect the metal parts of electrical equipment to the grounding electrode system. The bonding conductors must be sized large enough to carry the maximum fault current that could occur on the electrical system. The proper installation and maintenance of the grounding electrode system and the bonding system are essential for ensuring the safety and reliability of electrical systems. It is important to consult with a qualified electrician to ensure that the grounding electrode system and the bonding system are installed in accordance with the NEC and that they are properly maintained. The cold water piping ground is one of the most common types of grounding electrodes used in electrical systems. It is typically made of copper or galvanized steel, and it is connected to the metal water pipe that enters the building from the underground water main. The cold water piping ground must be installed in accordance with the NEC, and it must be properly maintained to ensure that it is effective in providing a low impedance path for fault current. The NEC requires that the cold water piping ground be supplemented by an additional grounding electrode, such as a ground rod or a ground plate. This is because the cold water piping ground may not be sufficient to provide a low impedance path for fault current in all cases. For example, if the water pipe is made of plastic or if it is not in good contact with the earth, it may not be an effective grounding electrode. The additional grounding electrode helps to ensure that there is always a low impedance path for fault current, regardless of the condition of the cold water piping ground. The cold water piping ground must be connected to the electrical system at the service entrance. The service entrance is the point where the electrical service enters the building from the utility company. The cold water piping ground must be connected to the service entrance equipment, which is the equipment that contains the main circuit breaker or fuses for the electrical system. The cold water piping ground must be connected to the service entrance equipment with a grounding electrode conductor. The grounding electrode conductor must be sized in accordance with the NEC, and it must be installed in a manner that provides a low impedance path for fault current. The cold water piping ground must be properly maintained to ensure that it is effective in providing a low impedance path for fault current. The cold water piping ground should be inspected regularly to ensure that it is in good condition and that it is properly connected to the electrical system. If the cold water piping ground is damaged or corroded, it should be replaced immediately. The cold water piping ground is an important part of the electrical system, and it must be properly installed and maintained to ensure the safety of people and property.